an honor today to have Marc, who is the director of the Phénomène supérieur. And normally one goes through all the awards that the distinguished speaker has had, but then starting 2 minutes early would not have been enough, so I will refer you to the flyer. I just wanted to encourage you also to come to some of the other Boole-Shannon events that we're having. This is an event that is being sponsored at MIT jointly by Electrical Engineering and Computer Science, Physics Department, the Research Lab for Electronics, and then outside MIT by the University College Cork. It marks the 200th anniversary of Boole, which is happening this year, and coincidentally, next year the 100th anniversary of Shannon is exploring those connections in a broad sense. So please do look at the website. We shall have a few other distinguished speakers. Another announcement is after the talk, there will be a reception on the 6th floor of building 36. And so as not to have a reception in the honor of a speaker who's not there, I shall be very adamant about taking the speaker there, and you can ask all your questions at the reception rather than here after the talk. So with that, thank you very much, Matt.
Thank you. Thank you, Miriam. Thanks a lot for this invitation. I really feel honored to be able to talk here on this occasion to celebrate Boole and Shannon. And in fact, I think it's a wonderful idea. I was slightly surprised that it was also run together with physicists, because in some sense, these are the two pioneers of information theory, computer science, and one may wonder what physics has to do with all that. Well, beside helping to build the computers that make all this possible. And I will try to argue that, on the contrary, physics is at the heart of this whole question of contemporary computation and information theory, in the sense that when you start to deal with large amounts of information, large amount of data, you have new phenomena which take place. And so I will bring some new actors into the game, and I have put here Boltzmann, probably the founder, one of the founders of statistical physics, and because I think that statistical physics has a lot to say and to discuss with other disciplines. Specifically, I will talk a lot about phase transitions, which has been one of the puzzles of statistical physics in the beginning of the 20th century, resolved, let's say, probably by Onsager and other scientists around 1940, 1950. And then there was a big step in the statistical physics of disordered systems around 1970 until now. And I think that this has opened a lot of exchange with other disciplines. But let me get back to Boole. I must confess that I was not so much familiar with the work of Boole himself. I mean, we know Boole as a kind of icon, we know the name, but very few of us have read it. So this invitation has given me the opportunity to start and go and read some of what he has written. And the introduction of the laws of thought, one of his main work, is very interesting. So you see, he states immediately what are his goal is really to understand the laws of thought. And he talks about the general laws of nature. They are either inductive inferences from a large body of facts, the common truth in which they express, or, in their origin at least, physical hypotheses of a causal nature serving to explain phenomena with undeviating precision. And then he goes on and they say that in all cases, and in strictest sense of the term, they are probable conclusions, approaching indeed ever and ever nearer to certainty as they receive more and more of the confirmation of experience. And this is why he starts to go to understand that. He starts to develop a theory of probabilities, of course, which is at the heart of what he's explaining in this introduction. The next paragraph is very interesting also, because he takes another point of view, different. On the other hand, the knowledge of the laws of the mind does not require as its basis any extensive collection of observations. It takes the exactly opposite point of view. the general truth is seen in the particular instance, and it is not confirmed by the repetition of instances. We may illustrate this position by an obvious example, and then he starts to discuss the maxim of all and none, de omni et nullo, the basic of logic in some sense. So this is very interesting. That is, he's addressing basically two ways of approaching the knowledge. One which is of statistical nature, empirical evidence, how it accumulates and then becomes more and more certain because of the facts that accumulate. And the other one which is some kind of fundamental approach, just logic, pure logic, let's say. And we will come back to that. I will put much more the accent about accumulation of data because I want to stress the point of view of statistical physics. A few decades ago, Phil Anderson summarized the purpose of statistical physics in some sense in a short article in 3 words. It was just, more is different. That's a wonderful title. It just explains that when you have many particles which are interacting, you get, as an outcome, something which is different from what you could have guessed. And the simple way of phrasing it is the following. Since Newton, we know the basic law that govern the world or the surrounding world, let's say Newton's law. If you are a bit, you look at some fancy phenomena, you will use Schrödinger equation. It doesn't matter for what I say here. Everything is known. You have the interaction between the particles, and you know the interaction law. Now, it still happens that you have this picture here. Still happens that at a very well-defined temperature, which is 273 K, you can have the molecules of water, which are either in a liquid state or in a solid state. And it matters a lot if you are on the boat which is driving towards this point. So how it comes? This was a big puzzle, whether it was due to a change of the laws of interaction between the particles or not. And it was completely understood already in 1944 by Onsager that it is not a change of the laws of interaction of the particle, it's a purely collective effect. It's an effect that happens only when there are many, many interacting particles. So this is the more is different. And so the problem that Onsager studied was a slightly easier problem, which is a problem of interacting spins. You have spins which interact. They are in a magnetic material. They can point up or down. The interaction energy is such that it is favorable for spins to be parallel, but then you have the thermal fluctuation, so they wander around, and so you have the Boltzmann weight, and you look at the collective behavior of this state of these spins. And what happens that above a certain temperature, they all fluctuate around, and you get zero magnetization. On average, the total spin is zero. There are as many which point up and down, up to square root of n fluctuations, of course. But then below a very well-defined temperature, which for iron is 1043 K, below that temperature, all of a sudden there is a collective phenomena and the spins point in the same direction. Still with fluctuation. There will be some which fluctuate, but the majority points up. And so you get a magnetized material. That is how magnetism is done. So it's called spontaneous symmetry breaking. It happens at a perfectly defined sharp transition. It's called phase transition. And this is the result, that if you plot the global magnetization of a piece of iron, above a certain temperature it is zero, and below this temperature it can take two values, one which is positive, one which is negative. Which one it takes, it depends on how you've prepared it depends on the impurities, it depends on the history. It will choose one. But once it is up there with magnetization, let's say 0.5, you will not spontaneously turn to magnetization minus 0.5. It's completely in this phase, and it does not change, except if the system is small. And that's actually an issue. If you are using magnetic domain for the memory of your computer, for instance, you have domain with 10 to the 4 spins or something like that, and that's okay. But if you go to domain with 100 spins, then you start to be in trouble because spontaneously they will switch from one state to the other. It means that the bit which was 1 turns to be 0. That can create a few trouble on your laptop. So this is one very important issue. So it's a purely collective effect. It's an effect of large numbers. In the 70s, there was an elaboration on all that, which was putting magnetic impurities in metals like copper and manganese. You put a few percent of manganese into copper. The manganese carries the spin, and the spins interact. It happens that in this case, the interaction between the spin, it's not like in iron where they want to point parallel, but the interaction depends on the pair of spins. You have impurities, and it depends on the distance between the impurities. So in some cases, they like to point parallel. In some cases, they like to point anti-parallel. So what happens in such a system is a very weird situation. First of all, there is a basic new principle, which is frustration. Imagine that you have 3 spins, and for each pair, the distance is such that they have a better energy. They prefer to be anti-parallel. So there is no way that you can have 3 spins and each pair being anti-parallel. So it's called frustration. The 3 spins are frustrated. It creates a lot of problems that it's not so easy to understand what is the configuration which minimizes energy. Actually, it's an NP-complete problem. At low temperature, what happens is that the system freezes, but with the spins which point in some random directions. And instead of having 2 states with the spins pointing up or down, you have many of them. And so it creates an extremely slow dynamics and a very weird phenomena. It's something that has attracted a lot of attention. It started in 75, in the 80s. There has been thousands and maybe tens of thousands of papers on spin glasses. It's still not completely understood. But it's an absolutely fascinating topic, and it has been named sometimes as a cornucopia. In spite of the fact that spin glasses, the real spin glass problem is still an open problem, what has emerged from all the studies on spin glasses in an enormous amount of concepts, of ideas, of methods that have proved very useful in other fields. Why is that? And so this is just a small cornucopia. Why is that? I try to explain it just in words. I have tried to avoid equations and things like that because just to be simpler. At the beginning of statistical physics, we were working with homogeneous systems. If you want to study an homogeneous system, that can be very fancy phenomena, but as a first approximation, what happens in an homogeneous system is that each atom, first of all, is the same as all the other atoms and sees the same environment. So you can use theories, which are called mean field theories, in which one atom is in the environment. It sees the interaction with the other atoms, which are the same as himself. So you use a theory which is a theory of a representative agent. You have one representative atom. It is the same as all the other ones. And self-consistently, you can say, if this atom has this or that behavior, the other ones have the same, and I write a self-consistent equation. This is called mean field equation. So it is, in terms of agents, it's the case where you have agents which interact with each other. Each of the agents has the same strategy, does the same thing. If you want to study the collective behavior, roughly speaking, there will be some subtle correlations and so on, but at the first approximation, you just work out the theory by saying there is a representative agent, and it is seeing the interaction from the other agents which are doing the same thing as himself. So you write a self-consistent equation. Now, gradually we have added disorder, already in the 50s and so on, and then after some time, we have started to handle strongly disordered systems like these spin glasses. So in a spin glass, each spin sees a different environment. So you cannot say that this spin here is the same as this spin here, because the surrounding spins are different. Maybe it is in a frustrated loop and the other one has no frustration and so on. So what you have to do is do something which is much more sophisticated, which is a statistics of representative agents. So you need to have a representative spin and another one and so on. And this has, so understanding that and creating the tools to mathematically analyze such a situation, this has opened the way of using these tools in very different situations, very different spins, atoms, or agents. For instance, if you work on the behavior of a market, if all the agents of the market are doing the same, again, you can study this relatively easily But the kind of thing that may happen is rather limited. Of course, you can have phase transitions, and you can have the market which goes. Actually, the more the agents do the same thing, the more likely it is to have a sharp phase transition. But if you have agents which have a diversity of strategies, then it is, first of all, much more complicated to analyze, but then you have a much richer behavior. And you have the dynamics, in particular, the dynamics of the evolution of the market is complicated. So this was just to give you, in some sense, my picture of why statistical physics has become a very important tool and why it is a cornucopia. So let me go to the phase transitions. I want to give you 3 examples of phase transitions in the fields that Boole and Shannon have created for us. The first one will be on error correcting codes. And the first transition that I want to address is the Shannon phase transition. So imagine that you want to send a certain message on a channel. It's a message of length n with binary alphabet, say. You have a noisy channel, let's say a binary symmetric channel in which each bit can be flipped with a certain small probability. And what Shannon taught us is that we should encode the message and then decode it. We encode it before sending it through the channel, and then we decode it. And encoding, decoding goes through a code book. That is, you look at all the possible messages that you could send. There are 2 to the n of them. It's a whole unit hypercube in dimension n. And on this unit hypercube, you select some specific words, which is a code book that you can transmit. And the other ones, you cannot transmit them. So you build this code book, and the code book is described by the set of the messages that you are allowed to transmit. And what Shannon studied in his famous 48 papers is a random code ensemble. Very easy. You draw this code book by picking randomly 2 to the L points on the hypercube. This is a code book. These are the words that you are allowed to transmit. And so this becomes a purely geometrical problem. You have your hypercube in dimension n, 2 to the n points. Among these 2 to the n, you select 2 to the L. And now what happens? In the thermodynamic limit in this case is taking n to infinity, very long messages, L to infinity, very large code book, with the ratio L over n, which is finite, which is called the rate. And you study the probability that by doing that, and you have a channel with a certain level of noise, study the probability that by doing that you are able to completely decode. The decoding is just very easy. You receive a message and you look at the closest word in the code book that you had. Now what happens if you look at the probability that the closest word in the code book with respect to what you have received was exactly the one that was sent? This probability is equal to 1 until a very sharp threshold. This is a phase transition. And then the probability goes to 0. So it means that below this noise threshold, the Shannon code works perfectly, and beyond that, it does not work. You're sure that it does not work. This is a wonderful statement. It's a statement about a phase transition. It's a statement about a phase transition in the, again, it's the more is different. It's in the thermodynamic limit, in the limit of large systems. There is a corollary to that Shannon also proves that you cannot go beyond. This is the absolute best code that can exist. You cannot go beyond that. So this is and the other point that I want to stress is that actually in Shannon, you are not studying one given code book. You are studying an ensemble of code book. You are studying an ensemble of code book in which the code book is generated randomly from a random process. Of course, in these code books randomly generated, there are some of them which are very bad, but statistically, you will never meet them. So this is a typical behavior with probability 1. If you generate a code book randomly, this will be the behavior. So this is very typical of what happens in disordered systems. We have the same thing in spin glasses. You put 1% impurities of manganese in copper. You can redo the experiment with another sample. It will be another disposition of the spins, but still you measure the same magnetic susceptibility, let's say. So it's called self-averageness of the system. So in this communication theory, there are many more phase transitions. So this was the Shannon phase transition. Now you can, there is a small drawback. The only drawback in Shannon's construction is that you cannot use it because the decoding takes an exponential time because you have this exponentially large number of code words. You want to know which one is the nearest to where you have arrived. This takes e to the n, 2 to the n time, basically. So you cannot use it. And so you start to devise other code books that are structured. They are not randomly chosen. They have typically an algebraic structure of some kind. So you start to work on Galois fields or something, or here I was taking the example, parity check codes in which you say that you are transmitting code words which are such that they satisfy some equations of parity checks have to be satisfied. x1 plus x2 plus x3 must be 0 modulo 2 or something like that. And so when you look at that in a typical structured code ensemble, for instance, LDPC, you look at the optimal decoding. You imagine that you have an optimal decoder. And again, it will have its threshold. It will have, again, a phase transition. It's the map phase transition which is shown here. Then, even in that case, generally, you don't know a perfect decoding algorithm. Perfect, I mean one which runs in polynomial time. And so now you go one more step towards practical building, and you look at LDPC code with iterative decoding. Well, you had Gallagher recently for this lecture. Probably, I don't know if he mentioned that, but he could have mentioned that, of course. We owe him this contribution, wonderful. So you have an iterative decoder, for instance, and again, it will have its own algorithmic threshold. So here is a system in which we have, for instance, LDPC code for transmission of a binary symmetric channel. We have 3 phase transitions. There is the optimal one, Shannon, cannot reach it. There is a maximum a posteriori probability. You cannot reach it in practically usable time. And there is a practical one, the one of the algorithm. So you see how phase transitions, how important are phase transitions. The first 2 ones are purely geometric ones, actually. And let me try to explain how these phase transitions go very pictorially. So this is an image of the unit hypercube in large dimension. I've projected it in 2 dimensions. And here I have drawn the code words as this lattice of points, let's say, just to say that they have some structure. And now there is one code word which is special, which is the green one. It's a code word that I have sent. It's a message that I have sent. It goes through the channel. After it goes through the channel, it is corrupted. There is a fraction, 0.1% of the bits which are flipped, let's say. So it means that what is received is at a certain distance, 0.1 of the original sent code word. That is what I received. Then now, if I know the channel, I know that with the probability going to 1 in the thermodynamic limit, the code word which had been sent was at distance 0.1 of what I have received. So I look at the distance, I draw my sphere of all the points which are at distance 0.1 from what I received. Now, on this sphere, there should be a code word. And if I find it, I have decoded. That's the rule of the game. Now, it may happen several things. Either there is a well-defined code word on this sphere, and the landscape around it is smooth. So it means that there is only one point which satisfies all constraints, and that you can find it relatively easily. Or it may happen, and that is something that we also see, it may happen that there is one code word. This we know that there is one by definition, but that there are also a lot of metastable states. What are metastable states? If I look at an energy landscape where the energy is the number of constraints which are violated, there is one which has 0 energy, that's the sent code words, and there may be some local minima which will trap the algorithms typically. And this will be a glassy phase. So let me try to be pictorially to explain you the geometry of the phase transition. So we have the easy phase where the algorithm easily finds a solution. It is the phase where you have just one code word on the sphere, and you find it easily because there are not so many traps on this sphere. So you get on the sphere, you can start to have more clever algorithms, but you can start to wander around on this sphere and you easily find the solution. Now there is this intermediate phase, and in LDPC it has been completely documented, that it is a phase in which the iterative algorithm, they run into trouble because of the proliferation of metastable states. So it is a phase transition in which we have the code word, it's like a crystalline, it's a crystal, it's a perfect situation that satisfies all the constraints. You want to find it, but there is a glass phase with a lot of traps. And this kind of slows down the dynamics. As in glasses, the dynamics of glassy systems, it's extremely slow. And then, of course, if you go beyond the threshold of the maximum probability, then you have a completely weird situation in which you have a lot of code words which are on the sphere or even within the spheres, and so there is no way to identify which code word was sent. So there is no hope. Okay, so this is just to show you that there is a direct correspondence, let's say, between geometry, phase transition, and the performance of an error-correcting code. So Shannon was working completely on phase transitions in some sense. Now I want to show a second example of phase transition. It is on the satisfiability of Boolean formulas. So there is a whole field of research in computer science which is called constraint satisfaction problem. And in this field there is a certain type of satisfaction problem which is called k-satisfiability. And k-satisfiability is very famous because it is at the heart of the theory of computational complexity. Actually, k-sat, satisfiability, was the first problem to be shown to be NP-complete by Cook. So it is a problem which has a very special status. It's a very easy problem to state, let's say, satisfiability. You have Boolean variables, so you have n, here I put zeros or 1, true, false or true. You have n binary variables, and there are constraints between these variables. And these constraints take the form of what is called clause. A clause is an OR function, so you have x1 or not x2 or x3. Okay, this clause is satisfied except in one case, in the case where x1 is false, x2 is true, and x3 is false, then the constraint will be violated. Okay? So this constraint excludes one configuration of x1, x2, x3. Now imagine that you take a large number, you take 1 million variables, and you generate constraints like that by drawing triplets of variables randomly. Take the 3 indices at random, and you build the clause, x131, x267, and 268, and you negate a variable randomly also. So you generate a random satisfiability problem. It's an ensemble, exactly as the ensemble that Shannon was studying. And then you can look at this problem and study the generic properties of an ensemble of random satisfiability formulas. Again, there will be a thermodynamic limit, a large size limit, in which you have many variables and many constraints, many clauses. And you take n variables, m clauses, and you fix the ratio, number of clauses per variable. Now, what happens is that if you look at generate randomly these formulas, and then you put that on your computer, and you look at all the possible assignments of the variable, you do that for relatively small size, and you look at what is the probability that a formula is satisfied, a randomly chosen formula is satisfied. And these are the curves which are there. There is a blue curve which is for 50 variables, the green one is for 100, and the red one is for 200 variables. And you see that if you have, alpha is the number of constraints per variable, so if you have relatively few constraints with a probability which is very close to 1, the formula is satisfiable. There is a way to assign the values of the variables to true and false that satisfies all constraints. If you have many constraints, you cannot satisfy all of them. So the fact that it is decreasing is easy. Now, the thing which is remarkable and that has attracted a lot of attention is that the curve becomes sharper and sharper. And actually, there is it has been actually shown that it goes to a step function, that is, it becomes a phase transition. for quite a few years, it was not known whether this step function was converging to a precise value. It could oscillate mathematically and so on. Now it has become clearer, and actually because of the use of statistical physics method on this problem. So there was what was called for a long time a satisfiability conjecture, saying that there is a sharp phase transition at a given value of alpha, alpha c. Above alpha c, for large size system, you are sure that there is no solution, and below alpha c, you are sure that there is a solution. So it's a phase transition of 3-SAT. Why has it attracted so much attention? Well, first of all, satisfiability, as I told you, satisfiability has a very special status. It's a core problem. But also, if you look at the time it takes to get this result over there, how is it done that? Well, it's done by some search, kind of exhaustive search algorithm in which you assign the value of the first variable, the second variable, and so on, until you hit a contradiction. If you hit a contradiction, you do some backtracking and explore another branch of the tree of assignments of the variable. And so at some point, maybe you can assign all the variables and you have found a solution, or you backtrack, and at some point you have explored all the branches of the tree and you know that there is no solution. That's how it works. Now, if you look at the number of branches of the tree that you explore, this is in log scale. So you see, first of all, again, there is a blue curve, a green curve, and a red curve. And so you see that in log scale, it grows exponentially, the computer time, to know whether a formula is satisfiable or not. It grows very fast. It grows exponentially fast. But the rate of increase is much larger in the neighborhood of the phase transition. So you have a much harder problem when the problem has been generated with a ratio of constraint per variable which is close to the phase transition. So the phase transition is not only a kind of attraction for the physicist who doesn't know what to do, but it's also first of all the way to generate very hard formulas. Now, exploring this with the methods and with the ideas of spin glasses, it was identified, first of all, that there is a phase transition. Secondly, that it is possible to compute the value of the threshold. So for 3-SAT, it's a result of a very complicated integral equation that I don't write for you because it would take a few slides and the end of the talk, so forget it, but the result is there. And much more interestingly, there is a phase diagram which is much richer. That is, this is drawn here pictorially. Again, alpha is the number of constraints per variable. So you have here the satisfiability threshold. And there are actually 3 phases. One phase is the phase below another threshold, another phase transition, which is called alpha D. And this is a phase in which the problem is relatively easy. Here on this drawing, it's very pictorial. Imagine that I am looking at, again, it's a unit hypercube in large dimension. I'm coloring in green the configuration which are satisfiable, which satisfy all constraints, and in red the not satisfiable ones. And what happens is that below alpha D, you have a big connected cluster of solutions. That is, you have a solution, you can find another one by flipping one variable, well chosen, and so you can go around, you have a connected cluster of solutions geometrically. It turns out that from the point of view of the algorithm, it's an easy phase. It's a phase in which you will relatively easily find the solution. Then there is this intermediate phase, which has been discovered thanks to the physics ideas, which was not obvious a priori. It's a geometric phase transition between alpha D and alpha C. What happens there is that you have regions of the hypercube in which you can find solution, but they are very isolated regions. So you have here a pocket of solution in which you have a connected cluster with a few solutions that you can jump from one to the other one by flipping a variable at a time. But then the other pocket of solution which is there is very far away. And it needs, in order to jump from here to there, you need to flip a fraction of all the variables. And finding the right fraction in n is, as you see, exponentially rare. So you cannot jump from one set of solutions to, so it's a clustered phase with many clusters of solution. And then above alpha C, there are no longer any solutions. So again, I try to, we like in physics to draw energy landscape. So this is a way to try to reason about the system. So in terms of an energy, which would be the number of violated constraints, the first situation when there are the number of, the fraction of constraints is below alpha D, it's a situation in which we have a big sea of solutions connected. And then maybe there will be some valleys somewhere else. But finding this big sea is not so complicated. There is this intermediate phase, which is a glassy phase, in which you have some small lakes of solutions at level 0, at the sea level, if you see. There are many of them, but it's very hard to find them because you have a lot of proliferation of mountain lake, which are not satisfying all the constraints. And then there is the unsat phase where you don't hit the sea level. All this was done around 2002. It was using this cavity method, which is a way to, it's a way to analyze what I was calling before the the statistics of representative agents. When you have a disordered system, what you need to understand is really the statistics of all the various representative agents. Here, the various representative Boolean variable. So you have Boolean variable, you have to understand their surroundings, and then depending on their conditionally to the surrounding of a Boolean variable, you will have its local property. So, and then you will have different property for another Boolean variable conditioned to its local surrounding. And you have to study all these statistics, and this has been done. This is what is called the cavity method. It is something that we call exact but not rigorous. It's not rigorous in the sense that it does not come as a theorem because it analyzes a system in the large N limit, typically by a kind of recursive way. That is, you go from a system with N variable to N plus 1 variables, and you understand how this change from N to N, like a recurrence relation, except that you cannot initialize it because all the properties that you look at are only in the large N limit. So it takes a lot of energy to convert it into theorems, and this has been done in recent years, since in the last 10 years or something, and all of this has been actually proven in the large K limit. For KSAT in the large K limit, there has been, in particular, recent work by Sly and co-workers who has settled this and shown that actually all these educated conjectures are correct, at least in the large K limit. On top of that, when you analyze this, this statistics of representative agent, as I was calling it, you can come up with an algorithm to solve K satisfiability. And this is an algorithm that we found with Riccardo Zecchina, who is here. And it turns out that it is an algorithm which is able to solve for 3 SAT up to the threshold, as far as we know. And it's a sophisticated algorithm that I will not explain in more detail. But it's also an experimental way. It's completely based on this structure, on understanding this structure in terms of glassy states. And it's a consequence of that. And the fact that the algorithm is successful and has not been, has not been challenged, at least since it was invented. There is no better algorithm known for this hard problem. So this is a kind of indirect confirmation, first of all, of the validity of the whole structure, but also of its practical efficacy. The third example of a phase transition that I want to give is a very brief allusion to compressed sensing. So here I get back to Shannon, and these are 2 pictures. I don't remember which one is which, actually. Probably the left one is the original one. I cannot say from here. Anyhow, imagine that it is the left one, that it is the original one. It has 65,536 variables. You do a wavelet decomposition of this image, and from this wavelet decomposition, you keep only 25,000, the ones which have the largest coefficients, and you get the right-hand side image. And you see that, to your eye, it's a good you have compressed the image, but it's a good compression. This is very well known. Every child knows that, literally, as soon as they have a phone or something, they are doing that all the time with their images, this kind of compression. Actually, it's something that is that you have to think about, but I would claim that all the interesting signals can be compressed, and therefore they are sparse in some appropriate basis. In this case, it's a wavelet basis. And this has been used for years about in order to compress the data. Now, the question that you may ask is whether you can use it at the level of data acquisition directly. That is, instead of acquiring a picture and then putting it on your laptop and then compressing it, can you, at the moment of acquisition, directly acquire only the relevant information and not the rest? This, if you are able to do that, you can speed up magnetic resonance imaging, you can speed up tomography, electron microscopy. It has obvious use for satellites because you use less energy to transmit the information. And there are many other applications. So this explains in some sense why there has been so much hype about compressed sensing in the last 10 years, that so many people have worked on that. It's a beautiful topic. And I will explain just one aspect of it, and I will talk about, very rapidly, I will talk about tomography. There is, to explain what tomography is about, I like this example. This comes from a paper of last year. These are carbonized handwritten papyrus scrolls gathered from Pompeii. And people have been working on those from many years, and they introduce, so here is how it comes. Here is how it is when it is cut. So it's rolled, it's extremely fragile. And of course, what people have done is invent some devices that will unfold them very slowly until you try to understand what is written on it, let's say. Now, of course, there is an alternative, which is to send light through it and see if you can read it without unfolding it. That's an obvious strategy. It's a very difficult one, but it has been done in recent time. And of course, there is something that can be very useful is if you can have prior information. For instance, if you know that what you want to read is a text, this is a very important prior knowledge that you can use in order to have better algorithm for doing that. So I have not worked on these papyrus scrolls, but we have worked on tomography of binary mixtures, which actually is much easier to explain. Imagine that you have a binary mixture. You have an alloy with two components. And you have this alloy, which is somewhere at something like that, and you want to know what is the composition. So you go to your favorite synchrotron, and you have synchrotron light going through it, and you measure. So it comes in here. I have imagine looking at it in a plane. Of course, you can have it in 3D. And so you have the synchrotron light, and basically what you do is that you have a camera with a certain degree of resolution, certain number of pixels. And so what you do is that each time you shine the light, you have L measurements. And the measurements tell you basically what is the absorption of the light along the channel that you are looking at. So here I have the light coming here, and on the pixel, it will depend on how much black and white. Imagine that the absorption coefficient is not the same for black and white. We will get an information which is just the proportion of black and white along the ray. That's relatively easy. Now, what is traditionally done is the following. So you have L measurement for each angle, and then you take your sample and you turn it, and you do L different angles. You have L square measurements, and you reconstruct L square pixels from that by something which is called the inverse radon transform. It's like the Fourier transform in some sense. That is, it's a linear transform. You have done a linear transformation from L square pixels to L square measurement. Very easy. Now, is it possible? Now, imagine that my sample is like that, and that the domain size, the typical domain size in the alloy, is much larger than a pixel. It's psi, and psi is large. In linear size, it's 20 times the pixel. So then it is very clear that such a system has a content of information, such an image, the amount of information in the image is not L squared bits of information. It's much smaller. Actually, I can give you a description of this image. It's something which is, there is a domain on the, at that angle with, I mean, I could write for you a description which does not contain L squared bits. That's much smaller. So can you exploit that? Can you exploit that in order to get the information without measuring L square pixel? And it turns out that this image, the one that I am showing here, digitalized on a 1,000 by 1,000 grid, can be reconstructed from a measurement of 16 angles. So 16 angles, each angle means 1,000 measurements. It means a speed up of a factor 60. So this allows you, a speed up of a factor 60 is something that is very sizable, okay? And you can understand why people are looking after such a speed up. Now, how you do that? Basically, you exploit two things. You can do it only on certain, if you have a certain knowledge of what you want to measure. Here, I'm an experimentalist. I'm looking at binary mixture. I have an idea that my system is a binary mixture. How do I use this knowledge? I put a prior, and my prior is the fact that I know that neighboring pixels have a certain tendency to be the same. So basically what I will build is, in kind of sophisticated term, I apologize for the jargon, but it will be an Ising model in which the neighboring pixels tend to be the same. That's part of the probability which is here. And then I put the constraint that for each measurement, I must obtain the sum of the spins on the measurement as obtained by the measurement. From this measure, can I get back the original picture? It turns out that for the picture that I've shown you, by exploiting this structure, I can do it with a speed up of a factor 60. If you analyze random instances, again, you will have phase transitions. And here is the number. Here it is the number of variables divided by the number of measurements. So in this case, basically there is the easy phase is when you have many measurements, of course. So when you have many measurements, you can do it easily. When you have not enough measurement, it's totally impossible. And in the middle, it's possible, but it's very hard. It's again a glassy phase, actually. And what happens is the following. You know, in this case, by construction, you know that there is a solution. You know that there is a set of pixels that satisfies what the constraint that you had put here, because you have measured this constraint. So there must be a solution. This solution, I call it the crystal. It's the one that satisfies all the physical constraints of my measurement. And now it may happen that if you look at again at the energy landscape, you have the easy phase in which you have the crystal and it's easy to find. You have the hard phase in which you have many solutions because you have not done enough measurements. You cannot, it's impossible to understand which was the structure. And you have this intermediate phase in which you have a crystal hidden somewhere, but then you also have this band of many glass states that makes life very complicated. So again, there has been a lot of work on trying to improve the algorithm to go beyond the first threshold and invade the second threshold. And this has been done, and it has been done using algorithms, sets of measurements which are such that you nucleate the crystal. That is, we know from physics that when you have a system which can be a crystal and a glass, if you want to have a very good crystal, one way to do it is to nucleate it. You nucleate it somewhere, and then you let the crystal grow. And that's exactly how it has been possible to get into this forbidden phase. Actually, the same thing has been done for error-correcting codes for the same reason. That is, you had one special state, which is a crystal, and the metastable states, which kind of ruin your basic algorithms. And if you can devise an error-correcting code which is able to nucleate the crystal, then you get much better solution. This is just to show you a few pictures. This is a picture of which is called the Shepp-Logan phantom. What we do with this picture is that we do a Haar wavelet representation. That is, we look at the sum and difference of neighboring pixels. So there are a lot of zeros because there are uniform zones. And so this is basically the second phase transition. This is the Shannon threshold. And what you see is three algorithms. One is the one which is called the L1 decoding, which is the one that has been used a lot since the invention of compressed sensing. And it stops at a ratio of number of variables to number of measurements. So actually what is written here is opposite. Number of measurements per variable, which is 0.5. And then you have the belief propagation case, and this gives you the second phase transition in the middle row. And this is a dynamical phase transition. And between the dynamical phase transition and the Shannon transition, there is a glass phase. And the bottom line is what you are able to do when you nucleate the crystal. So you get around the glass phase, you get through the glass phase, because you nucleate your crystalline state and you decode it. So this is the same picture with a nicer character, just to show what happens. And I want to spend the last 5 minutes or so in order to go away now from slightly away from the phase transitions, but they will maybe come back at some point, and go into some somewhat more speculative ideas that I want to share with you on this occasion. Okay, the right-hand side is easy to describe. It's a picture of myself on my vacation in Tuscany last Christmas. Okay, never mind. The left-hand side is my book. It's my last book with Andrea Montanari. I have it on my laptop. It uses an amount of memory, the full book, of 5 megaoctet. The picture has 5 megaoctet also. So now, I've always wondered about that, actually, in some sense, because this book, it has 22 chapters, 100 of exercises. Some of them are not simple at all. I mean, I know quite a few very smart colleagues who have worked on it and who have, have spent a lot of time on that. And it probably, I don't know, but there are a few hundred people who, maybe 1,000, no, a few hundred people who can read the book. And some of them take the book and they do a lot of things out of it and they create a lot of knowledge out of the book. And the picture is totally useless, except maybe for my children, but there is no way to use this information. So there is this question of knowledge and information. And I am not blaming Shannon. I mean, each of them is 5 megaoctet. I know what it is. Now, there is something in it, and which is, as I told you, it's very speculative ideas in some sense, but never mind. I think that there is something in it which has not yet been totally enough explored, that there is some kind of, there are various types of information. That is, in the book, you have a very structured information, and it is an information of a combinatorial nature. It's kind of book of physics, theoretical physics and mathematics, so it comes with pieces, and then you combine these pieces and you build a new piece and so on, and you elaborate by combination. And you combine and you elaborate, and that's how you do math. I mean, you have the lemma, and then you have another lemma. From that, you get a theorem. And in some sense, you will say that you get out only what was in at the beginning. You are not creating new things, but still, you are creating knowledge. Maybe you're not creating information. Everything is in the axioms of the theory. But you are creating some new knowledge by combining these various pieces of information. And this is not possible on the image. So another way of saying that is people often go to people who study big data. They always talk about the curse of dimensionality. So if you have an image with 10 to the 6 pixels and 128 gray levels, let's say, you have a number of possible images which is 128 to the 10 to the 6. A large number of images. You would say, well, what can I do with that? How can I recover an image or something? On the other hand, on YouTube, for instance, you find, I quote my source, you find this small thing which tells you how to draw George W. Bush in 15 seconds. So in 15 seconds, out of these 128 to the 10 to the 6, you extract one that everybody recognizes in the room. So now you can understand, you can argue about that, saying that maybe George W. Bush does not contain much information. The picture, I mean, the picture. That's possible. Actually, that's probably true. And, but still, I think it's the same thing. That is, in some sense, there is the amount of information is something that is still has to be worked upon. And I want to finish with an example that has been studied a lot in recent years. If you look at the top sequence, every child beyond I don't know, at 7 years old child or something, we recognize a sequence of digits. Say it's 504192. Okay, good. The child recognizes it through a certain number of devices, which are its neurons and so on. And it turns out that this has been a relatively big challenge for computers to try to do the same. And some breakthrough have taken place thanks to several ingredients. It's a problem that was studied using neural networks already in the 80s. And gradually it started to work in more recent time for two reasons. One reason is that the amount of data available has grown, and of good data. And this is something which is very important. So you have now data with a few tens of thousands of images of digits, well calibrated, segmented, and so on. And the other ingredient is the fact that the computers have gone faster, so that you can run the algorithms that were not possible to run in the 80s when we were studying this kind of problem. So basically, in terms of what you want to do, you want to look at this. You want to look at this picture on a 28 by 28 grid, and out of that, you want to have an output which is it's the number 5. Okay. So one way of doing that is using a neural network in which you have neurons for each of the incoming pixels, neurons at the output, and you have some law for how a neuron is working. And typically what a neuron does is it computes an output which is a function of the weighted sum of its inputs, and the function is a kind of sigmoid function. That is how a neuron is working. Now, what people are doing is building typically a 3-layer network. The input layer is just the image. It has its 700 and something neurons. The output layer is the 10 possible digits. And in the middle, you put a layer with 15 neurons, for instance. Well, you try 15, 40, 137. You try several numbers that you like. And what you do now is that you train this network on your database of these few 60,000 images, and you train it by trying to find out what are the weights, this famous weighted sum that I was mentioning. And so you do the training and then you test, and it happens that by doing that in recent time, these devices have become able to really work as good or even better than a human being in identifying the digits. Let's say they miss only a few of them, but this is because in the database there are really bad digits like this one. I have no idea what it can be, but okay. So how does the neural network infer the result? It infers the result by building internal representation. This intermediate layer is absolutely crucial. We know that without the internal layer, we know that it is not able to do the job. And so again, actually this has gone now into a whole more sophisticated program which accumulates these intermediate layers and gone into what is called deep learning. And the reason why this is working so well on practical application is not yet very well known. But I'm convinced that, again, it has to do with this combinatorial organization of the information. That is, in some sense, the various layers, they will do, it's a caricature. We know that it's not exactly like that, but they will start to extract some feature, and then the relevant combination of the features, and then the relevant combination of the combinations of the feature, and so on and so forth. And so this is another example of showing how a neural network in this case is processing the information. And again, I am pretty sure that there are phase transitions at work in this system, but they have not yet been found. But we will find them very soon. So in deep networks, you solve these complicated systems. And there is one big question, and I want to finish with that. Can one learn from watching the machine? We have this machine. It has a huge database. It learns. At some point, it comes with the weights. You have these weights, and it does what you wanted it to do. Can you learn something out of that? Can you look at the internal representation, understand what are the features or something like that? It's something very basic. It has to do with the way we do science. Another example is DNA chips. You have a microarray. You can monitor the expression of 10,000 genes for something in many cells. Now you can do it in individual cells. Looking at that, you can do correlations between this expression of genes and a certain cure for a disease, and you have personalized medicine. So this is the way that medicine has been going, actually. It starts with the blood groups. You had 4 blood groups, and then it gets more and more sophisticated. Now you have thousands of genes, and you correlate that with a cure for a disease. So you get a purely statistical way of doing medicine in some sense. Okay, perfect. If for myself, it's fine. I mean, if the statistics is good, I'm happy with that. But at some point, I think that there will be this challenge, which is, can one learn the mechanisms? Can one understand what is happening by looking at what the statistics has found? And so I think that it is bringing us to some kind of interesting issues about the way of doing science. About the whole scientific method, and I wanted to finish with this picture of Galileo studying free fall. So it has been for a long time that science is working by some dialectics between experiment, modeling, theory. And in some sense, I think that there is a new ingredient now. It is the fact that by doing this statistical approach with many, many variables, we are no longer, probably for the first time, we are in the position where we scientists, we don't select the variables that we want to look at. In some sense, the statistical system will tell you out of the 1,000 variables, we suggest that these 10 variables are the most important ones. And then we'll have to decipher and start to understand how the system itself is working. And this brings me back to the laws of thought, and I think that I could have mentioned again the introduction of the book of Boole, because that's in some sense what he had also in mind with these 2 aspects, which is the statistical aspects on one hand and the aspects of pure logic on the other hand. And okay, I think I'll finish with that. Thanks a lot.
So the case where you have easy, hard, and impossible, the hard part seems to be there is a phase transition in your hard part, but it's first order as opposed to second.
Yes.
Is that right? If you get the nucleus, it grows from that nucleus. Mm-hmm. So the hard part is to find the nucleus.
Yes.
That's usually a first order.
Yes, it's a nucleation problem with the first order phase transition, that's true. But what makes it very hard, it's not the fact that it is a first order phase transition, it is the fact that there is, simultaneously with this crystal, there is these glass states, which are really, basically what you want to do is nucleate the crystal and avoid the glass, which is something that happens in a lot of physical systems, actually, if you think about it. You can do it typically by doing 2 things. One is very slow annealing, and that's the whole strategy of simulated annealing and so on, but it's just much, much too slow a process to be useful for any of the practical issues that I was addressing now. And the other one is to devise in some sense, well, if you are looking at communication, you divide your set of parity check, or if you are looking at compressed sensing, you devise your measurement, the set of measurement, in such a way that you will get around the glass, that you will naturally crystallize the system. In compressed sensing, you do that by having a certain number of measurements which focus on a subgroup of the variables, so that you have enough variables for this subgroup, and so you start to fix in the right direction a fraction of the variable. From that, you have the nucleus, and the system invades the whole system.
Can you maybe give a few examples of, like, all of this are equilibrium phase transition, of non-equilibrium phase transitions in these kind of non-physics?
Yes, yes, I have avoided to enter into the dynamical issues, but they are there completely in all the talk, actually. As soon as I talk about a glass phase, really the characteristic of the glass phase is that there is an infinitely long relaxation time. That is the way that these metastable states, they affect an algorithm, in my case, or dynamics in the physical system, is that it makes the dynamics of the system infinitely slow. And that's something that you have seen. It has been seen, for instance, on spin glasses. You take a spin glass, a simple piece of copper manganese. You have it at 12 Kelvin below its glass transition. And depending of whether you have prepared it yesterday or the day before yesterday, if you measure it, you don't see any change a priori. But if you measure its response to an external perturbation, you can see what is its age. So the system is aging on and the typical natural time scale for the spin flip is 10 to the minus 13 seconds. So you see the system is aging on a very, very long time scale. And it's because there is this proliferation of metastable states that the system is going from one to another one near to it and so on and so forth. So all these dynamical issues are of crucial importance, but I could not take the time to explain them.